All right, good morning. Hopefully I have technology working. All right, let's see. Chat questions. Yes, you can go over 100% on PA3, and if you underperformed on another assignment, then those points are added on that. If you do perfectly on every programming assignment, then you would get over 100% on the programming assignment percentage of the final grade. So it just adds in as points in the programming assignment category, and it builds from there. So yeah, you don't lose anything for being perfect. Interesting question. Having a kind of ongoing turn things in early bonus. Um, it's not a bad idea. I don't think I plan to do that right now, but it's something I'm kind of considering. Um, yeah, I'll think about it. I would like to do anything I can to encourage people to work on their assignments sooner rather than later. But I mean, this is the nature of time management, right? Which I don't know about you, but I always find it challenging. Um, if it's going to take you, 5 hours to do something, I can spend those 5 hours now. I can spend them, in the 5 hours before it's due. It's the same amount of work, right? But if I put it off, number one, I spend, all the time before then feeling bad that I'm not doing it. And then number two, of course, if it takes longer than 5 hours, I miss a deadline. But, that's really easy to explain, really hard to change, though. I mean, we're just kind of wired, I think, to put things off. Quick question about parsing. Will it be perfect if it works exactly like temp PA3? Yes, that is absolutely correct. So on the sample code on PA3, so you use the command S to switch to stack mode. If you type, SSSSS, hello, ha ha ha, it takes that as an S command and switches to stack mode. That's perfectly acceptable, right? So really all you have to do is check the first character of the input. And so let's talk about parsing, because this has come up a bit lately. Parsing on these assignments, right? We need to be able to manage different kinds of inputs. Maybe the person types a number, maybe they type a character, right? Or maybe in other assignments they're supposed to type a character followed by a number. And you want to get fluent in being able to work with different styles of input like this. So first of all, the whole reason that we talk so much about scanf is this business of two tasks we have to do when we're writing, say, a main program. We have to input stuff from the user, and then we have to interpret it, okay, or parse it. If you use scanf, these happen at exactly the same time. One call to scanf, and it reads input and it parses it. I knew I was missing something. There we go. Thank you. All right. So scanf does input and parsing at the same time. And what we really want to do is we want to split these into two separate tasks. So you do your input with fgets, and then you do your parse with scanf. And an advantage of doing this is, you know, we can scan your input multiple times in different ways. So main program call fgets. That basically says, you know, wait till the person hits enter, tell me what they typed. And now we have an array, a buffer in memory that has the user's input. Now we can start analyzing it, parsing it. So what do you want to do for PA3? Here's a simple view of your main program. Get some input. Okay. And then, is it a number? If it is, either push it or insert it into the queue or stack and go back up here. If it's not a number, is it an S command? If it is, set your mode to stack mode and go back up here. If it's not, you know, was it a pop command? If it is, are we in stack mode? If we are, pop, go back up. If we're not, then remove and go back up. And if it's not a pop command, go on and see what else it might be. Alright, I'm only worried about the parsing part here, so this is just for example, right? But, you know, read the input. You do that once. Let them type some stuff, hit enter, and now I know exactly what they typed. It's in memory. I can do all kinds of things like that, right? And I'm just working with this one copy of what they typed in. So let's see if it's a number. If it is, let's either push it or insert it depending on what mode we're in. If it's an S, let's go to stack mode. If it's a Q, let's go to Q mode. If it's a P, let's either pop it or remove it depending on what mode we're in. If it's an uppercase Q, let's quit after freeing memory. If it's anything else, let's give them a help message. So this is one way to split it up. So how do we get the input? That's fgets. How do we know if they typed a number? That's scanf. So try scanning their input with a %D format, and if scanf returns 1, you've got a number. If they didn't type in a number, scanf will return something different from 1. Could be 0, could be -1, but it'll be different from 1. How do we know if they typed something starting with an S? Well, here's an easy way. Let's just look at the first character. So if their input starts with an S, let's go ahead and change our mode to stack mode. How do we know if they typed something that starts with a P? Let's look at input 0 and see if it's a P. And so on. Now this is a forgiving way to check for commands because anything they type that begins with an S will be treated as a stack command. Anything they type that begins with a P will be treated as a P command. What do you mean by an overflow string? Oh, you mean the extra stuff at the end? I'm happy with anything that starts with an S is S. Anything that starts with a P is a P. And that's what the sample code on the server is illustrating also. If you wanted to check this and make sure it's exactly an S, what can you do? See if input 0 is S and input 1 is a null terminator. That would be one way to do it. Another way would be to you know, do a string compare to the literal string double quote s followed by a new line, because fget puts a new line on the end, and things like that. But this is perfectly acceptable. What you don't want to do is go a little overboard with scanf, though. Right, I've seen code where people are doing an scanf with a %c and a space and a %d and a %s, and then analyzing each of those parts and pieces. That's too much work, right? Let scanf do the work for you, which is really converting an integer, right? And then for the other stuff, you've already got a string of characters. You've already got access to the first character, that's just input bracket 0. Just start using that, right? Should we check for extra characters in the event of something like 135? You mean like 135 characters? So remember, your input gets truncated by scanf automatically. For popper remove, should the number print from the function or return the number and print it from main? I would return from the function and print it in main, because you want to be developing the idea of a queue package and a stack package, and so you know, don't print from inside those routines. Just like you don't want to print from inside your linked list code, you want to return, you know, something. But I'm not going to check for that, right? So do what makes sense. Number followed by extra spaces. Nope, you can just take that as a number. So if they type 23 space haha, just push a 23 on the stack or insert it in the queue. Don't even worry about the haha. My goal here is, you know, to let you spend your efforts on the stack and the queue and the linked list, and not have to spend too much of your time worrying about the parsing. Now in 224, we spent a lot of time with much more complex user interfaces and error checking and things like that. But here, you know, I want to be more focused on the data structures part. So I'm kind of relaxing the guidelines for processing input and error checking and so on and so forth. Doesn't mean you should get sloppy for the rest of your life with it, right? But for now, focus on the data structures. But I will test your input by typing ha ha ha, and it should say, you know, illegal command or show me a help message or something like that. If I just hit enter, right, that's not a legal command, so show a help message. But I'm not going to try to, you know, type an 80-digit integer or type, you know, 12.7 and you know, expect an error or something like that. So pretty straightforward. Let's see, in your demo code, when I try to print an empty stack, it prints stack is empty without printing the stack. But when I try to print out an empty queue, it actually prints out the queue instead of printing a message. So I would do your code exactly like that. Okay. All right, good. Other questions? All right, so back to tree traversal. Yeah, make your output look like what the sample code is doing if you don't want to have to think about it. There's possibly ways that you can interpret the grading rubric that would let you get away with doing something different. But if it matches what the sample code is doing, you're guaranteed to be all right. If you already did it some other way and it matches what's in the assignment itself in the grading rubric, then you'd be okay also. But I don't want to try to dissect that right now. Binary search trees. There's a totally random tree. There could be winning lottery numbers in there somewhere, but I doubt it. But maybe I should go get a ticket anyway. Totally random search tree. Here's the root. We want to look at the question of tree traversal. So remember, traversal is just a fancy way of saying let's visit every node. Let's move through all of this stuff that we've got in here. And let's, for example, print out the contents of every node. With a linked list, it's straightforward. Start at the first node, print that, move to the second node, print that, move to the third, print that, and so on. It's just a simple loop. With a tree, it's a lot more complex because at each point we potentially have two different directions we can go in. And for example, if I go off to the right here, now I've got two more directions I can go in. I could come down here or here. And these can have, you know, pretty complex structures. So we want to look at ways that we can go through the data in a tree and visit the nodes, right? Encounter them and perhaps print them out, or, you know, maybe add them to a list or search for something or whatever. And so I want to look at a traversal method called LNR, which means left, node, right. And this is also called in order traversal. And this is also an example of depth first search, DFS. And this is also stack based. So a lot of buzzwords on here, right? But we're basically going to call this a left node right traversal. And here's the high level idea of how to visit the data in this tree. Left node right means the following. We've got a root that we're starting at. The first thing we're going to do is traverse the entire left subtree of that root. So we're going to ignore all of this, and we're going to say, hey, let's visit all the nodes in this tree. So that's the first step. Second step, we're going to visit the root of the original tree. And then third step, we're going to say, let's visit all the nodes in this right subtree. If you have a function for visiting all the nodes in a tree, this is really easy. Call that function on this tree, print a 60, call that function on this tree. It's 3 steps. But, you know, there's the question, how are we going to visit all the nodes in this tree? Well, it's the same 3 steps. First, visit all the nodes in the left subtree. Then print out the root. Then visit all the nodes in the right subtree. So suppose our tree looks like this. If we wanted to do this left node right traversal, what does it mean? First, let's visit everything in this left subtree. Well, there's only one thing in the left subtree, that's a 45. So that's step 1. Step 2, let's visit the root node. That's a 50. And then step 3, let's visit everything in this right subtree. Well, there's only one node in there, which is a 52. So this would be the in-order traversal for this node, this tree containing 3 nodes. And if I had another tree containing 3 nodes like this, well, it would be the same exercise, right? I'd visit everything in the left subtree first, which is a 7, and then I'd print the root, and then I'd visit everything in the right subtree, which is a 14. Okay, now that I know how to traverse this tree and how to traverse this tree, suppose I have the following tree. Right, a tree with 7 nodes. And I want to traverse this in left node right. Well, what do? First, I look at the left subtree of the root, that's this thing, and I say, let's visit all of these nodes in left node right order. Well, we've already done that. We know that if this is our tree, LNR is going to give us 7, 10, and 14. So I'll write those down. And that's the whole traversal of the left subtree of the root. That's step 1. Step 2, visit the root node. That's just a 40. And then step 3, do a left node right traversal of the right subtree. Well, we've already done that. 45, 50, 52. The traversal should give us 45, 50, 52. Well, there's the left node right traversal of this tree. Two things to note at this point. Number 1, these are always coming out in order, right? That's why this is called an in-order traversal. If it's a binary search tree, you know, where everything to the left is smaller, everything to the right is bigger, doing this LNR traversal will display your data in increasing sorted order. That's one thing to note. The second thing to note is that, you know, if I had a bigger tree that had, you know, this larger structure on the left, right, and I wanted to traverse, you know, this as part of some larger tree, right, I know how to do that now. So we're building up to the notion of recursion. We'll get there either tomorrow or Monday or Tuesday. But before we go down that rabbit hole 100%, let's play around with this and think more from a high level perspective how we can traverse this, right? The truth of the matter is the way we're going to traverse this is always to do 3 things. Traverse the left subtree, print the root node, traverse the right subtree. But let's think about what that's actually doing. What does this actually look like? So we start from the 60, and before we print the 60, we want to traverse the left subtree. So we want to look at this, which means we're going to start from the 40, but before we print the 40, we want to traverse the left subtree of the 40, which means we want to start with the 20, but before we print the 20, we want to start with the left subtree of the 20, which is a 5. So we're really going left, 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 left as far down as we possibly can. And the first node that we print is going to be the thing that we get by just going left as far as we can. And then after we've printed that 5, we're going to pop up 1 level and print out the 20. That'll be the second thing. And then we're going to go to the right and we're going to repeat that whole process. We're not going to print 35 next. We're going to start going to the left and go as far as we can and then print the root node and then come down to the right. And if there was more stuff over here, we would start traversing that by going to the left. let's see, what if we get the data in order, then everything will go to the right nodes? Then it will just be a linked list without benefits of a tree. How do we stop that? That's a really good question. And we will start talking about that tomorrow for sure. What we're going to discuss is what's called the balance factor of a tree. And the notion that all three of these trees have the same data, and they're all binary search trees. But these are really just linked lists. And this is a nice fluffy tree that will give us really good behavior when we want to search for things, whereas these are going to be order n. And so the question is, how do we avoid ending up with stuff like this? Well, that's going to be a long discussion, but it's what we call balancing a tree. And it's ways that we can take this or this and turn it back into looking like that. And we will definitely go over that and write some code to deal with that. And that'll be kind of the highlight of CSE222, right? That's going to be kind of the penultimate data structure manipulation. I don't use the word penultimate actually, so I just faked it. But yeah, so we'll spend time talking about that. All right, so left node, right traversal, right? The feeling is we move really far to the left, and then when we can't go any further left, we just pop up one level, but then immediately go back down and start trying to go left again. And we're going to do that in this repeating fashion. So let me put our tree aside and give you some pseudocode. Now this won't be the pseudocode we end up using when we actually code tree traversal. We'll use the recursive approach in the end. But let's see what's happening with the recursive code. So let's do left node, right traversal. And it's a bit of a quirky algorithm. So it's stack based. So first thing we do is we push the root of the tree onto the stack. All right, and then we enter a main loop. And our loop says move left as far as possible. Pushing nodes as you go. So we're going to start off, we're going to start moving left, 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 and each time we move left, we're going to push that node onto the stack. And then we're going to enter a subloop L2, where we're going to say pop whatever's on the top of the stack, print it, and then if the node has a right child, we're going to push it and go back to our main loop. Otherwise, we're going to go back to L2. Alright, so see the algorithm by pushing the root, and then move as far left as possible and push onto the stack as you go. When you can't go left any further, pop the stack, print it, push its right child, and go back up here. If there's no right child, just go back to L2. So let's try that with this monster of a tree. So I'm going to make a stack. I'll put the top of the stack at the top of the page. So I'll start inserting things down here and building our way up. And so what's our algorithm say? First, we push the root onto the stack. That's how we seed the entire process. So we put a 60 there. And let's keep track of our output. So we'll assume we're going to print our data. All right. So what do? We start moving left as far as possible, pushing nodes as we go. So we'll come down to the 40, push that. Come down to the 20, push that. Come down to the 5, push that. Now we can't move any further left than the 5. So now we come to step L2. L2 says pop the top of the stack and print it. And then if it has a right child, push it. Well, there's no right child to 5. So we go back to L2, which says pop the top of the stack and print it. And then if that node has a right child, push it and go back to loop. Okay, 20 has a right child, 35. So let's push a 35 here. And let's go back to the loop. Our loop says move left as far as possible, pushing as you go. So let's go down to the 27, push that. That's as far as we can go. So now we're at L2. It says pop the top of the stack and print it. And then if that node has a right child, push it and go back to loop. 27 has a right child, 31. So let's push that onto our stack and go back to loop. Loop says go as far left as possible, pushing. Well, there's nothing here to the left of 31. Notice though, if there was, I would be doing all of this stuff on that left subtree before I print 31. This is this recursive left node right. Okay, well there's nothing to the left of 31, so I can't push anything and move left. So I go to L2, which says pop the top of the stack. So I pop off the 31 and then print it. And then if the node has a right child, push it. Well, there's nothing to the right of 31. So I'm going to go back to L2. Okay, let's look at where we are right now. We've printed out a 5, 20, 27, 31. 5, 20, 27, 31. We haven't printed the 35 yet. Where is it? It's sitting on the stack. And after we print the 35, we're going to go to the right and start dealing with all of this stuff. And only after we finished all of this from here on down will we pop off the 40, print that node, and then we're going to deal with all of these. And only after we finish dealing with all of this stuff will we pop off that 60, print the root, and then start dealing with the right subtree. Right, this is quintessential stack. And this is quintessential depth first search. We are moving deeper and deeper into here. We came up a little over here and we immediately started going as deeply as we could before we came back and moved over to say the 38, which we haven't done yet. And we're going to do all of that before we start exploring these nodes. Right, so this is depth first search. We're going really, really far down. If we're maze running, this is trying to get as far from the beginning as possible. Trying to just keep going in whatever directions and get further and further and further. And if you have to back up as little as you have to before you can start making more decisions. And in the example of running a maze, you know, if in the very beginning we first got into the maze and we could have gone left or right, we started off going left. We're never going to come back and try going to the right until we've explored every possibility that we have from making that first left turn. Same thing here. We start off by moving to the left. We're going to visit every single node that we can get to, having first gone to the left, before we come back here and go to the right. So yeah, the stack really does help make this easy, because I've been talking for like 3 minutes now, and I can go back and pick up right where we left off because the stack is preserving the information for us. Alright, so we were at step L2. L2 says pop the stack. So we'll pop off the 35 and print it. And then if the node has a right child, push that and go to loop. 35 has a right child, 38. So I'll push that on the stack. And we go back to loop. Loop says move left as far as possible. There's nowhere to move left. So pop the top of the stack. That gets rid of the 38. Print it. And then if it has a right child, push that. 38 has a right child, 39. We'll push it on the stack. And we'll go back to loop. Loop says move left as far as possible. We can't go anywhere to the left. So pop the top of the stack. That's 39. Print it. And then if that node has a right child, push it. Well, there's nothing to the right of 39. So we'll go back to L2 and pop. What are we going to pop now? We're going to pop off this 40. And we're going to print it. And then if that has a right child, push it. So 40 has a right child, 50, so we'll put 50 on the stack. And all of this stuff is gone from our stack now. But I'm going to start writing up there. So push the 50, go back up to loop. Alright, move left as far as possible, pushing as you go. Pop the top of the stack and print. So we pop the 45 and we print, nothing to the right. So go back to L2, pop the top of the stack and print. And then if it has a right child, push it. Well, 50 does have a right child, 52. So push that and go back to loop. If there was stuff to the left of 52, we would start doing that, but there's nothing to the left. So pop, print. And if 52 has a right child, we would do stuff. Otherwise, we go back to L2. What do we pop now? We're going to pop off the 60. And look at what we've output. We've output everything in this left subtree of the root. So we finished our first L, our first traversal of the left subtree. Now we're going to pop off the 60 and print it. And then if that has a right child, push it and go back to the top. Well, 60 has a right child, 80, so we're going to put 80 on the stack and go back to the top. Well, let's stop here and collect ourselves. What have we done? We traversed the entire left subtree, printed out all those nodes, and we just printed the root of the original tree. And now we took an empty stack and we put an 80 on it. Our situation right now is exactly the same as if you had been given this tree and asked to traverse it. What would you do? You would push the root onto the stack, and you would have a stack containing one thing, which was an 80. And you would be sitting here at the beginning of your loop. So I won't go through the remainder of this, but I think you can see that if we do this, right, it's going to do exactly the same thing on this subtree. And it will end up, you know, printing an 80, a 100, and then when it gets here, it'll print a 120, a 130, a 135, and then it'll come up to a 140. And when we finish with that, we'll try to pop, and there won't be anything left to pop. And so when we pop, we can say if the stack is empty, then you're done. So this is perhaps an uninspiring algorithm. This doesn't necessarily, you know, ring as like, oh yeah, that makes perfect sense. But mechanically, if you do what this is asking you to do, you'll start to see that, you know, what we're doing is this left node right business, where left means do left node right on this, where that means do left on this, and then do left node right on this, and then print a 40, and then do left node right on that. And like I say, when we start writing code for traversal, we're going to do something much easier. But underneath, this is what's going to be happening. There's going to be a stack which is going to be keeping track of where we are, so that when we've done, say, left node right traversal of this, we'll know what to do next, which is come back one level, say, well, we just finished right, come back another level, we just finished left of 40, let's do the node of 40, and then let's do the right subtree. And when we finish that, we'll come back here and say we just finished the left subtree, let's do a 60, and then do left node right on this. Is that making some sense? Cool. So stacks and queues. Yeah, so if you look at this in assembly language, when you write this recursively, you're really doing the same kind of thing. That's a cool observation. But we'll possibly start talking about recursion tomorrow. If not tomorrow, then definitely Tuesday. And we're going to start getting into this in 2:15 at 12:30 today. All right, so this is depth first, and when you do this in order traversal, your nodes come out in order. That's why it's called in order, assuming this is a binary search tree. But we also have the option of using a queue. So we can do queue-based traversal. And the algorithm is a little easier. The algorithm is as follows. First, insert the root. And then we have the following loop. So we insert the root, as usual, at the tail. So remove whatever's at the head, print. Insert that node's left child, and then insert the right child, and then go back up to loop. Only do this insert if the children are not null. Don't insert null. If there's no left child, just don't insert anything. If the queue is empty, then you're done. So here's a simplified tree, because we only have 3.5 minutes left. Oh my gosh. All right, so let's see what this does. So here's my queue, and I'll remove from the left and I'll insert at the right, and we'll keep track of the output. All right, so we start the whole thing by inserting the root of the tree. And our loop is just the same thing over and over and over again. Remove the head, print it, push its children. All right? So we remove the head and we print it. And then we insert its left and right children. Well, left child is a 40, right child is an 80. Go back and do it again. Remove the head node, print it. Insert its left child, that's a 20. Insert its right child, that's a 50. Go back and do it again. Remove the 80 and print it. Push its left child, while left child's null, so nothing to do. Insert its right child, which is 100. Go back to the top. Remove the 20, print it. 20 has no left child, nothing to insert. 20 has no right child, nothing to insert. Remove the 50, print it, insert the left child, insert the right child. remove the 100, print it, nothing on the left to insert, insert the right child. Remove the 45, print it, nothing on the left, nothing on the right. Remove the 52, print it, nothing on the left, nothing on the right. One thing left in the queue, it's almost empty. Remove the 140, print it, insert the left child, no right child at 140. Go back, remove the head of the queue and print it, insert the left child, insert the right child. Remove the head of the queue, print it, no left child, no right child. Remove the head of the queue and print it, no left child, no right child. Try to remove the head of the queue is empty, we are done. And what's the significance of the order in which the output appeared? Right? We started at the top and we moved down. It's definitely not ordered in the sense of, increasing from smallest to largest. But the first thing that we printed was, the node at this top level. The 40 and 80, those are all the nodes at the second level. 20, 50, 100, those are all the nodes at the third level. 45, 52, 140, those are all at the next level. 130 is everything at the next level, and 120, 35, those are at the deepest level. So this is not depth first, but breadth first. We move all the way across and print everything at this level before we go a little deeper. And then we visited everything at this depth before we went a little deeper. So this is a BFS. And typically when you use a stack, you get something depth first. When you use a queue, you get something breadth first. And this is useful if you wanted to actually, physically print a picture of the tree. You would kind of want to, print it from top to bottom, which means you want to see the top nodes first, and you'd probably want to see them from left to right. So you could physically print, a 20 and a 50 and a 100 and so on. And so a queue-based traversal works well for that. Not any way that I know to use a stack as a BFS and queue as a DFS without, in the process, somehow changing your stack into a queue and vice versa. I think it's kind of intrinsic to the nature of LIFOs and FIFOs, but I'm not positive about that. It would be a cool thing to contemplate. All right, so tomorrow I want to look at some more aspects of trees, and I want to start looking at order of complexity of operations and see why trees give us better performance than linked lists, and look at ways that we can assess how good our performance will be on a tree. So we'll look at heights and depths, and this will bring us into the notion of balance, and back to the earlier chat question. And we'll look at some other traversal orders that we can do, and then we're going to start moving into the recursive version of these things, and that's where things get really good. So that'll be our game plan starting tomorrow. All right, have a good one, and I will see you next time. Thank you.